Okay, we're going to talk about RC circuits. This is a really interesting subject because with RC circuits, you really see where, theoretical physics or mathematics really helps us out and lets us understand something that, it's not totally obvious, or not. I don't mean totally obvious, but it's not part of common sense, I would say. Also, we were joking around when we were building the robot. Varun was coming about, so you wait 5 tau. Okay, remember that? You always wait 5 tau. 5 tau, or as he said on the Facebook page, and I can't quote it completely here, but 20 tau, or it takes him 20 tau to wake up or something in the morning. I don't know. We're going to learn what tau is today. So that's pretty cool. So now an RC circuit is very well named. It's a circuit that has a resistor and a capacitor in series with each other. And these kinds of circuits are common. They're used all the time. So here's a circuit we're going to be dealing with. We've got a battery or some kind of voltage source. And then you've got, and it doesn't matter what order you put them in. You can put, we'll just put a resistor right there and a capacitor right there. And so here's our resistor and here's our capacitor. Here's the EMF from the battery, and we'll just assume the internal resistance is negligible. Now, one thing we need to put in here is a switch. We're going to put a switch in there. So what we're going to do is we're going to talk about two things: a charging capacitor. Now what this means is that you start with the switch open like this, and there's no charge built up whatsoever on the capacitor. And then you close the switch, and here's what happens. You get a rush of current flowing through it, and then it starts filling up that capacitor with charge. And once the capacitor is filled up, you've got no more current in there. But it takes time for that to happen. How much time depends on the resistance. If you have a lot of resistance, if your resistance is really big, it's going to take a long time, to fill. Tau is going to be big, okay? But if your resistance is really low, that's going to allow a lot of current to flow at first, and so your capacitor is going to fill up really fast. So how much time it takes to charge a capacitor depends on how much room there is on the capacitor. The bigger the capacitor, the more charge it can, so the more time it's going to take to fill up. And also it depends on the resistance. The greater the resistance, the less current there is, and so the longer it takes to fill that capacitor. And that's what we're gonna study here. Then what you can do, and this kind of makes the circuit look complicated. I should change that switch around. Let me change the switch. Is a discharging capacitor. Okay, we're going to study that. Now, this is just what you think it is. It means that you're going to discharge this capacitor, but you have to cut the you have to cut the battery out of the circuit, and the way we do that is we have a bare wire like this, and so here's my switch, and here's when the circuit is open. Then the switch can go here, and when it's here, it's a charging capacitor, and then I can move the switch to here. And when I do that, when the switch is put like this, notice that the voltage source, my electric cell, it contributes nothing. It's like it's gone. And so let's say you have a capacitor that is fully charged, and then you close the switch like this, boom, all this charge is going to be released out of the capacitor, but it's going to take time. And again, the amount of time, if the capacitor is big, that means it's got a lot of charge on it. It's going to take more time to discharge, right? Or if the resistor is really big, It forces the charge to come out in a little trickle, and it's going to take a long time. So the bigger the capacitor and the bigger the resistors are, the more time it takes to completely discharge. And by discharge, I mean it's got no more charge left on it. Okay, so let's analyze a charging capacitor. So let's charge one up here. Okay, so now let me erase this back and forth. I know this is not a fair thing to do for you taking notes, but oh well. So let's say it's like this. At t equals 0, you close this switch. Now what we're going to do is we're going to analyze this using voltage man. Okay? So voltage man is going to walk around the circuit the instant this thing is closed. Now that's the superpower that voltage man has. Voltage man can go all around the circuit faster than the speed of light, instantaneously, and measure all the voltage drops at any instant in time, everywhere in the circuit. No, I don't know. Now, so here's voltage man here, and you go boom like this, and you've got a voltage increase. Now, if you go over here, you've got a voltage drop, right? You've got current flowing through it, and that voltage drop has got to be equal to this voltage increase. But what about, is there a voltage drop across the capacitor? Not at t equals 0, because there hasn't been enough time for there to be any charge. Now let's review where voltage drops come from. Here's our resistor, and we've got current flowing like this. And so this, when you go with the current, you know, think of a capacitor as being like a little waterfall, okay, a little waterfall. The water's falling down, it's losing its energy. Energy is exiting the circuit right there. If you're going, now, if again, remember when, if you're going against the current, it's like you're a salmon swimming upstream. You have to jump up the waterfall. But here we're going with the current, so you're going down. So this is a voltage drop, and the voltage drop depends on I times R. I mean, the voltage drop is IR. Now, if you have a capacitor, we have a voltage drop. And this voltage drop, well, we define capacitance as being Q over delta V. So delta V is equal to Q over C. So the voltage drop depends on how much charge. Look, this depends on how much current. This depends on how much charge. And again, it's a voltage drop because there's positive charge here, and you're going with the electric field. Whenever you go with a field, you're losing potential. Okay? And so it's a voltage drop. But at t equals 0, there isn't any charge on the capacitor. All right? And if there's no charge on the capacitor, there's no voltage drop. So where is all the voltage drop? Across the resistor. Yes? No, it'll stop. This acts like a, and the question was, once the capacitor's full, does the charge keep going, or?
What about the voltage?
Okay, if you wait a long time, this is an excellent question. If you wait a period of time long enough, you know, more than 5 tau, it will essentially, the current will essentially be 0. And so voltage man will go around the circuit and go, oh, voltage increase. If the current is 0, there's no voltage drop across the resistor. So all the voltage drop will be across the capacitor. And if you're in between, if you're somewhere in between, and that's what we're actually going to look at, then there is some voltage drop across the resistor, depending on the current, and some voltage drop across the capacitor. Okay, so let me continue here. So let's go through this. We have a voltage increase. Voltage man starts here. Whoop, we go up in voltage. We go around the circuit. Woo, minus IR. And then we go woo down here, minus, let's see, Q over C equals 0. So we're back where we started. So this is the voltage equation. I go up in voltage, I go down in voltage to get back to 0. Okay? Now, we want to analyze this equation. And when we do, well, we can see that I equals dq dt, doesn't it? Okay, so all I did was redefine this. Now what I'm going to do is I'm going to solve this for I'm going to solve this whole thing for dq dt. Okay, so let's divide everything by r, and when we do, we get e over r minus, oops, so we divided it by r, so it's gone, minus q over rc equals 0. Now, I want to analyze this before I move on. What is dq dt? What is this term right here? It represents my current at any instant in time. Okay? Now, I'm subtracting it from this, and I'm, this is getting subtracted. So every term has to be current, doesn't it? You see that every term has to be current. You can't add current. You can only add or subtract currents. Okay, you can't subtract chickens from dogs, okay? If you got a bunch of dogs, you can subtract some dogs, but you can't subtract chickens from dogs. Yes?
So initially we had all voltage difference, we divided everything by resistance, we made everything current.
Exactly. Everything here is a voltage. You divide by resistance. That turns everything into currents. Now, what is this E over R? What is this? Or, yeah, this is our current at t equals 0. Okay? Now, and this, now let's take a look at this. Look at this right here. Q over RC. Q is our charge at any given instant in time. So this has coulombs, right? Well, what are the units for current? It's amps, but what is an amp? It's a coulomb per second. So if this is coulombs, what units does R times C have to have? Seconds. And it does. It does. This is that famous tau that some of you on the robotics team have been hearing about. This is it right here, R times C. Now let's figure that out. Let's show that it has units of seconds. First of all, so R times C. Well, remember that we said that R is an ohm. And, well, if I look at Ohm's law here, I can say that an ohm is a volt per amp. Okay, so that, now I'm just looking at units here. And C is capacitance, and that's a coulomb per volt. A coulomb per volt. Well, what happens to the volts? The volts cancel. Now, what is an amp? An amp is a coulomb per second. So this is 1 over coulombs per second times coulombs. And what happens is that this will cancel. You get 1 over seconds, which is seconds. So when you multiply the resistance times the capacitance, you get a single value of time. It will be in seconds. It'll be like 3.1 seconds. And we have a name for that amount of time, and we call it tau. And it is a measure of how much time it takes to discharge a capacitor. And we're gonna come back to tau, but I want you to see that you can learn a lot by analyzing each term in an equation like this. Okay, so now we will solve for dq dt. Just put this on the other side. You get dq dt is equal to, well, let's see, that would be E over R minus Q over RC. Now this is a differential equation, and I want to solve this differential equation. I want to find the equation where when you take the derivative of it, you get this. Okay. So, and I always mess this part up. So what I want to do is I want to get all the Q stuff on one side and all the T stuff on another side. So let's multiply top and bottom here by C, and then I've got a common denominator, and I think we get C E minus Q over RC. Okay. And now what I'm going to do is I'm going to put dt over here, and I'm going to put this down here. So I'm going to put dq over CE minus Q is equal to dt over RC. Now I don't like this. I want to get the Q in front. So this is kind of an arbitrary thing. I'm just going to multiply both sides by -1. And when I do that, I've got a sheet of paper here. I get dq over Q minus CE equals negative dt over RC. Okay, now what I want to do is I'm going to integrate both sides. Now this side I'm going to go from 0 to some time t, and I know that mathematicians don't like using the same number here. Oh well. All right. Now we're going to talk about charge. We're integrating charge over here. And so how much charge was on our capacitor at time, 0? There was 0. We're going to go from 0 charge to some charge of Q. Now, this side's pretty easy to integrate, isn't it? Okay, this side is going to be negative T over RC. But when you integrate this side, you are going to get, from 0 to Q, you're going to get a natural log. Like this is like dx over x, isn't it? Now, I'm just going to go through it really quickly because the integration isn't that important. Just kind of accept that this is the integral. We get, you get Q minus the capacitance times the EMF of the battery over negative CE. So this, when you integrate this, you get this from 0 to Q. When you integrate this, you get this. Okay, now we want to solve for Q. We want to solve for q. So I need to get rid of the natural log. So what am I going to do to both sides? How do you get rid of natural log? Yeah, raise the power of e. So I'm going to raise this to the power of e. So this becomes q minus ce over negative, oops, that's okay, ec, equals e to the negative t over rc. And so now I'm going to solve for q, so I'm going to multiply by negative ec. So I get q minus ce equals negative ce times e to the negative t over rc. And this is just pure math now, okay? So now I'm going to add ce to the other side. And so q is equal to, am I still on camera? Barely. So now q is equal to ce minus ce times e to the negative t over rc. Well, this is, I can take one more step to simplify it a little bit. Let's factor out the ce. The charge is equal to ce times 1 minus e to the negative t over rc. Okay. Now this looks crazy, but this is a beautiful thing right here. Okay, this is an exponential function. Exponential functions are some of the most important functions in all of science and business. You know, I mean, we in biology and sociology, and look, here's where we started. Let's go back to the very beginning, or almost the very beginning. Let's take a look at this. Whenever you have an equation where within that equation you've got the quantity and the first derivative of that quantity in that expression, you've got when you solve the differential equation, you get an exponential function. In other words, this q is going to depend on the rate at which q changes. And when you get that, you have, when your speed depends on the rate at which you change your speed, you have an exponential function. When your money depends on the rate at which you change your money, you have an exponential function. If you make an investment and you make 10% per year on your investment, the money you have as a function of time depends on how much money you started with, but it also depends on the rate at which they add money to the money you've got. Interest rates. So by the way, all of you who are going to go on and study business someday, you should understand, you're not going to have to solve RC circuits. If you're going to go into business, you're probably not going to worry about RC circuits, but you are going to deal with exponential functions all the time. They're the most important and most neglected functions. They are. It's kind of sad. All right. Now let's analyze this mathematically. Let's graph the charge as a function of time here. And this graph is, you're going to see it on the test, you're going to see it all the time. Okay. When t equals 0, what is this going to be equal to? Just look at, you don't have to do any calculations, you just have to think. Plug in t equals 0 into this equation, and what do you get? 0. Because what is e to the 0 power? 1. And what is 1 minus 1? 0. So this correctly says, hey, you're going to have no charge on your capacitor. There's no charge stored in the circuit at t equals 0, which is exactly right. Now, if you wait a long time, many tau, well, okay, here's t. Here's r times c. There's my little tau thing. What if I have many, many, many multiples of tau? That means you're going to have 1 minus e to the negative power. Well, what happens? Well, let's rewrite this so it's a little bit easier to see. Q is equal to CE times 1 minus 1 over e to the t over RC, right? I got rid of that negative, and when you get rid of the negative here, you do that by making it a, 1 over it. Does that make sense to everybody mathematically, right? So what happens when t gets really big? What happens to this term? It goes to 0. As t goes to infinity, this term goes to infinity, but it's 1 over infinity, and 1 over something approaching infinity is it's approaching 0. Yes? So this is going to go to 0. This part goes to 0 as time gets really, really big. Well, what is 1 minus something approaching 0? 1. And so that means that Q, the charge on the capacitor, will equal C times E. Does that make sense? Yes, it does, because what we're saying here, let's go back to our original thing. When you allow the capacitor to fully charge, the current will go to 0, and what will happen is all of the voltage drop will be across the capacitor. And that's what this equation is saying. If you wait long enough, essentially all of the voltage drop, E, right, the total voltage of the circuit will be the voltage across that capacitor now, will be, the charge on the capacitor will be the total voltage times the capacitance. Now we never really reached there. We're going to call this CE. This is my maximum charge. So we start with 0, and what happens is that we get an exponentially shaped curve. And we approach it but never quite reach it. Now, we use a particular value of time. Yes?
Okay, so at time 0, is capacitance 0?
No. The capacitance, remember, is the charge on the capacitor is 0.
Oh, okay.
But the capacitance is just a function of this device. I mean, it's a function of its area and the distance between its plates and how much gunk, what kind of gunk you put between the plates, right? So that doesn't change with time. The capacitance is a constant.
Okay.
It's, yeah. And so now we've got this. Now, here we have, we're gonna just do this arbitrarily, because look, you say, oh, how much time does it take to fully charge a capacitor? Well, you look at this, you say, well, it takes an infinite amount of time. Well, that is not a satisfying answer. We need some way of describing how much time it takes to fill a capacitor. So we say, what up here might be a good way of describing how much time it takes? Well, look at this RC. Let's let T equal RC. Well, okay, plug it in there. So Q is equal to CE times 1 minus e to the negative RC over RC. Well, what's RC divided by RC? It's 1. So really it's 1 minus e, 1 over E. Okay, and when you do that, you get this, I believe, when you take your calculator out and go 1 minus 1 over E, you get 0.632. I'll leave it to you to plug that in your calculator and check it. So that means that my charge is 63.2% of my maximum charge. Well, what is 63? It's right about there. So there's RC. This is the time axis. We showed that R times C is a measure of time. So when I let T equal to R times C, the charge on the capacitor will be up to here. So when you say, what is the tau of this? Or let's say you say let R times C equal 2 seconds. You multiplied R times C and you get 2 seconds. Well, that means that in 2 seconds, the capacitor will have about 63% of its total charge. If you wait another tau, you go 1 tau, this is 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. It's essentially full. So when they say, how much time does it take to fill a capacitor? Well, you say, well, what's tau? Well, what's R times C? Okay, you get a certain value, a certain amount of time. And you say, well, multiply it by 5, and you can say, it's full already. Okay, now it's not quite full, but it's 99.9% full. And if you wait 20 tau, well, now you can get out of bed. All right. And that's an inside joke. All right. Okay, so we have now an equation for the charge accumulating on the circuit for a capacitor. Now what about the current in the circuit? Well, current is just the derivative of charge. So let's do that. So let's find the current. Well, we said that Q is equal to CE minus CE times e to the negative T over RC. This is the equation for the charge accumulating on a charging capacitor. Well, let's take the time derivative of this. dq dt is my current, and that's going to be equal to, well, what's the derivative of that? It's 0. C times E is a constant. The derivative of a constant is 0. So now we just have to deal with this mess. Negative CE times, well, we got to take the derivative of the inside part, right? I got to use the chain rule. So what's the derivative of negative T over RC? It's negative 1 over RC. And then we have what the derivative of the outside part is just, remember the derivative of what's the derivative of e to the x? E to the x. Woohoo! Yeah, that's the neat thing about exponential functions, is that their derivatives are just the same. It's the same thing, but you got to use the chain rule too, so it makes it a little more complicated. But it's negative T over RC. See, all that stuff you learn in calculus, it actually is useful in the real world, not just the math world. All right. So the current, now here the negative sign cancels and the capacitance cancels in here, and you get E over R. Does that make sense? E over R? Heck yeah. And then we have times E to the negative T over RC. Well, does this make sense? Here's my equation. This is it. This is my answer. This is current as a function of time. Does this make sense? Heck yeah, it does. Look. When you try to graph this as a function of time, current as a function of time, well, plug in 0. What do you get? What's e to the 0 power? It's 1. It's e over r. Yes, that makes sense. Let's go back to my original thing. When I close this switch, there's no voltage drop across the capacitor. All the voltage drop is across the resistor. So we instantaneously have, the current is at its maximum at t equals 0. The moment I close that switch, I get my maximum current, which is E over R. Then we're going to get a like this. Now, as t goes to infinity, this term, this factor in the term goes to 0. Thus, the whole thing goes to 0, and you get this. And if you go to tau, and we use this little Greek letter tau, we say tau, by definition, is R times C in an RC circuit. We're going to do LR circuits later, and they kind of behave the same way, and they have a different time. This is called the time constant right here. Time constant. It's a way of measuring how long it takes. Now, if you plug in tau, if you plug in RC over here, you have E over R times E to the, or 1 over E to the 1 power, or actually totally E to the negative 1 power. And when you do that, E to the, 1 over E is 0.368. This is 0.368 of E over R. So, and by the way, this makes sense in another way. Let me zoom out a little bit. Just think about taking the derivative of this. It looks like this. Because look, where's my maximum, the slope of this curve is my current. So look, maximum slope, right? And then the slope gradually approaches 0. The slope over here isn't quite 0, but it's approaching 0. And that's exactly what I have over here. And so, yes, this makes sense. So this equation describes the charge accumulating on a charging capacitor. And this function describes the current in the circuit. And they absolutely make, if you can look at the circuit, and really think about what's happening to charge as it's flowing and accumulating on the capacitor and moving through the resistor and all that, it totally makes sense. If you just try to memorize a bunch of equations, it's going to be very difficult. But if you think about voltage man conserving energy, going around the circuit, measuring voltage changes, and then you do the mathematics, you get these crazy equations here. But the mathematics makes conceptual sense when you actually think about what's happening on an RC circuit.